Hi roboticists, in today's video we are diving into one of the most important concepts in robot motion planning, especially when we are talking about industrial application. And I'm talking about obstacle avoidance in ROS2 integrated with Movit. And what I'm going to do is that I'm going to start and show you how Movit integrates sensor data from the camera that we have simulated in our environment that publishes a topic of type point cloud, and Movit is able to integrate this data in Octomap from this 3D camera so that the robot can adapt to dynamical obstacle in real time. Then we will see the advantages and drawback, and we will start by looking into how Movit understand also the robot environments, and then we will learn how to add a collision object directly from code. And this represents things like tables, walls, or any obstacle that your robot needs to avoid in order to do a proper planning. So before to start, make sure to subscribe to the channel, hit the notification bell in order to do not miss the next topic. Okay, there we go. Let's jump into our simulation. So this is the environment that we have already created in the last video. I'm gonna put the link in the top right corner. Okay, so what I want to show you is how to Movit gets the data from the camera and publishes an Octomap. Okay, so this is RVs. Okay, so let's open a little bit here. Okay, so most of you might already seen this cube. So what are these cube? Well, this cube is the Octomap that Movit translates from the topic that the camera is receiving. Okay, and so basically it says that the camera talks to the Movit and tells already the space that is not allowed for the robot to go. Otherwise, we're gonna hit some obstacle. Okay, and okay, you can, if this bother you, for simplicity, if you want to get out from here, you need to go to motion planning, scene geometry, and then this is gonna be the voxel rendering, so you can disable it. So, but the fact that you're gonna disable it doesn't mean that Movit don't take into account. So even if it's disabled, Movit takes into account the object that the occupied voxel tells. Okay. In fact, what we're gonna do is to try to reach a position to take the object, to pick the object. Okay. So just put this side by side. Okay. Then let's ask to the robot to go in the home position, and then we are trying to picking this object. Okay, so what we're gonna see here, this is the first problem that we are going to face. The fact that this Octomap is too coarse, it doesn't allow us to reach the exact position. This is because these little cubes are not well defined. Okay, so in fact, if we are going to go down a little bit because we are too far from taking the object, you can see here that if I plan and execute, okay, move it doesn't allow me to reach that position. Why that? Because the Octomap says that if I go in that direction, the gripper and the robot is going to collide with the object. Okay, but this is not the right thing from the reality, right? Because we have still some clearance, right? So this is something that this is the drawback of the Octomap. So, before to find a solution, I wanted to show you that you can still use this Octomap to avoid some course obstacle. So imagine, for example, that let's suppose that we have picked our object, okay, and let's see that let's say that we want to go in the bin, okay, and so what I can do here is to try to go in this position, and we are gonna see what's happened. So we are gonna see that if we go in this position, okay, the fact that this is red is meaning that it's colliding, okay, so this is okay, but what I wanted to show you is something very nice. What I want to show you is that if the Octomap allows you to go in a certain position, and you can see it because the robot it's orange, so it's not marked in red, it's meaning that this position can be achieved for the robot. Okay, so what is happening if I go plan execute? Well, the robot is going to the target position, avoiding the wall of the object that we have put. Okay, and we don't need to do nothing. Okay, we have let move it to do his work. Okay, so basically if we were able to pick the object, then we just needed to ask the robot to go in that position, and then the camera, thanks to the fact that it's publishing a message of type camera points, move it, translates this topic into a Octomap, and this allows you to run as default an algorithm of obstacle avoidance, okay, because the straight away motion planning will be to go exactly from here to here, but since that we have this Octomap that move it is getting from the camera, then it's gonna do this pathway. Okay, even though this is not the right manner to run this motion planning, because we weren't able to reach the target position by picking the object, I wanted to show you this very useful tool from Move It, because you can run very easily an obstacle avoidance by letting the camera doing his job, or better, transmit this data to Move It. Okay, where you had able to do this? Well, do you remember when we have created our Move It config package? If no, I'm gonna put the link in the top right corner. But we have created our motion in our Move It configuration package, and then we have set up our sensor 3D on file. Okay, so basically here I said that the topic that the camera is publishing is this one, and from this topic that has to be depth sensor, okay, we are going to use this sensor plugin that basically is able to create an Octomap based on the free data that the camera is streaming. Okay, So this is a very useful tool, I will say, but we have seen this drawback. Okay, this is very useful if you have a robot that is moving in the environment, and the obstacle change over the time. Okay, and then this is important to have this functionality. By the way, you can check out these parameters in order to make your Octomap thinner with the cube thinner. Okay, but this is out of the scope of this video. If you want to get some fun, you can try to tweak this parameter. Okay, what I want you to think about is that this very useful tool, we need to understand when it is the case to apply them or not. In a mobile robotics is going to be very useful because the obstacle change over the time. But in an industrial application, I don't think that it's useful to. But if you are running an industrial application where we have the object, the obstacle that we want to avoid that are in a fixed position, I don't think that this Octomap feature is useful because I'm consuming computational resources from the ROS environment in order to calculate this Octomap, and find a way to make a inverse kinematics that is avoiding this Octomap and is constantly calculating this Octomap. And so I don't think that is a smart solution. Okay, so that's why I think that is better, smarter, to hard-coded this obstacle as a collision object. Okay, what I wanted to show you is to run this obstacle avoidance without using this Octomap monitor. Okay, so in order to do that, in our launch file, don't worry, I'm gonna put the link in the top right corner, I have modified this launch file in such a way to give some kind of flag, and if it's going to be as default, there's going to run with the Octomap. But if this argument is going to set up as false, we are going to run our application without the Octomap, or basically we are going to run without the sensor 3D file that MoveIt is automatically getting from the MoveIt configuration package. Okay, and the fact that you have created this MoveIt config here, okay, and you have spawn your MoveIt group like this, is automatically, if you don't do nothing, taking the file sensor 3D YOM file. Okay, so I have set up another node that I've called move group no map, and basically if this is gonna be false, I'm gonna run the launch file without getting the data from the camera. Okay, so let's see what is happening. Let's run this this launch file, but with Octomap that is gonna be false. Okay, what's happening? Okay, there's always our application that is here. Okay, but if we are gonna see in RVs, we don't see the cube, we don't see the Octomap. Okay, That because this time move it is not seeing the file, the YAM file sensor 3D. Okay, so this means that I still have the camera that is publishing on the topic camera points, but Move It is not considering this. Okay, so for example, if we can add a camera, and then with the camera we are going to put the topic image row. You can see that here you're gonna see the camera. Okay, so it's just a matter that Move It is blind to the camera. Okay, we are not interested in this at the moment. So what I wanted to show you is to hard code the obstacle. Okay, and we can see that we have this table, we have this basement, and we want somehow to hard code this box, but in an intelligent way. Okay, so let's see what I've done here. So if you go in the package, for which I remember you're gonna have the GitHub repository. This, I remember we have seen last time, which is the inverse kinematics, where basically it's just a simple code that allows your render factor to go in this position. Okay, what I did is to create this file here. So let's put it. Sorry for this. Let's put it here. Okay, I have created this file here, and basically is exactly the same, but with the difference that I have added this collision object. There we go. So I added this part here. Okay, so basically we have created a collision object message type that belongs to this class. Okay, and then I have put resize 4 because we are going to have 4 objects that I'm going to have table 1, the basement to which our robot is lay on, and then is wall 1 and wall 2. What is wall 1 and wall 2? Where this is wall 1 and this is wall 2. Okay, of course you can do a very complex geometry, but for the point of this YouTube video, I wanted to show you a very basic collision object. So I have created the table, I have created the basement, and I have created the wall 1 and wall 2. Okay, so let's see what is happening if we are running this node here. You can see here that you are going to have the table, okay, the basement, that is this one, and then I have created this wall here that represents the bin that I have created in the last video. Okay, of course you don't need this to be very precise, but at least you need to have the key collision object that represents the reality. Okay, and in this case we are presenting the simulation environment, so it's not precise, but is just only to let you know how it's work. Okay, it's normal that the robot go in this position because it didn't touch the position of the end effector from the last video. So what we can do here is to see if the fact that we have hard-coded the collision object is going to be more precise, right? Then let's ask the robot to go in the home position here. There we go. So Now, what you need to know is that now move it is not considering the Octomap, but is considering the collision object that we have hard-coded here. And you can see here from the green part here. So now let's see if we can reach this object. Okay, so you can see here that you are more precise. Well, because if you hard code the things, then move it. It doesn't need to make the effort to calculate the Octomap based on the sensor that the camera is streaming. Okay, so now what I want to do is to run a pick and place application. So let's suppose that we wanted to grasp here. Let's do it very very small closure because I don't want to struggle with the um, uh, gazebo um, the gazebo parameter for sleeping, for avoiding the sleeping. Okay, so now what I'm gonna do is to simulate the picking by tricking the physics as we have seen in the last video. Attach link object, there we go. Okay, we have it, so we can call the service. I have already explained you how to use that. Check out the video. Okay, so it's true, so meaning that the object is fixing to the gripper. Okay, so now let's go for making a picking. Okay, and let's ask the robot to go in this position inside the bin. Okay, and theoretically move it is gonna see that there's gonna be an collision object. Okay, in particular this wall one that we have hard coded, and let's see the kind of motion planning that is gonna do based on that. Okay, and let's ask the robot, for example, to go directly here. Okay, you can see here that now is switching from orange to red, of course, because we are colliding. Okay. Let's put in this position. Okay, so theoretically, we are good because from the collision object that we have hard-coded, it seems that the robot can reach the target position because it doesn't collide with anything. Okay, of course, the better the collision object that you have hard-coded represents the reality, the better the simulation will work. But let's see what's happening by plan and executing. So basically, there we go. So you're gonna see that the robot is reaching the target position, avoiding the wall that we have hard coded. Okay, there we go. So it's exactly in the target position. And then what we can do here is to just place is just to place this object, and we are gonna call the detach link should be this one, the touch link. There we go. So the robot reaches the target position by considering the wall of the Bing that we have hard-coded as a collision object, and the motion planning plugin of MoveIt planned the trajectory of our robot, or better, the end effector, accordingly without colliding the object. So we have seen today that we have two manners. The first is letting MoveIt do everything. So let's move it to read the sensor 3D YOM file that you have set up in the MoveIt configuration package in such a way that MoveIt is taking the data that the camera is publishing, and it calculates its own Octomap. Okay, and this is very useful if you have some objects that are dynamically changed over the time. Okay, but if you're gonna have some objects that are static with respect of the base link, most likely you're gonna have this kind of scenario in an industrial application, then I would suggest you to save some computational effort from your machine and code a collision object, a hard-coded collision object, into your inverse kinematics algorithm. Okay, that's all for today. I hope that you enjoyed this video. I think that today we have add a little brick in your experience in ROS. And again, this is only the top of the iceberg. And if you want to learn how to become a robotics software engineer, check out the link in the description down below. That is gonna bring you in the masterclass that is specifically designed to let you transform in a robotics software engineer that is able to run industrial application with the 6-axis robot with computer vision integrated. Okay, so feel free to check. We are going to run this kind of simulation with two different pipeline in OpenCV and Point Cloud for 2D and 3D. Feel free to check out the module, and I'm gonna publish one module, one per month. And well, let's say feel free to it's gonna be a subscription. Feel free to have a look. And again, if you like this kind of video, make sure to subscribe to the channel, hit the notification bell, and as always, keep learning robotics with Ross.